machine learning. It keeps on growing at a relentless rate. As StemDevops, we were tasked with developing a solution, a model that is capable of identifying brain tumor and categorizing them accordingly. Hence, now we'll take you to our solution. And now let's move on with the code overview. So the data that was given to us was basically a set of images, which you can see here. And the files were categorized into 4 categories: no tumor and 3 types of categories, basically. So that is the input we used as well. So with that in mind, let's go into the code. So in here, so the first thing you see is the necessary imports that was given, and it is followed by the respective 4 categories. So we got it in an array called categories, and then on we can proceed to the computation. So we basically divided the dataset that was given into 3 sections: train, validation, and test. So the reason behind choosing 3 processes was basically to increase the accuracy. So rather than using just train and test, we used a validation as well, hence providing the model the opportunity to validate itself and increase the accuracy even more. So as you can see, the train ratio was basically 80% of the dataset that was given, and followed by the validation ratio, which was 10%, and testing 10% again. So then we basically resize the images into 224 by 224, considering the fact that that was the smallest images available, and also because it is way easier to process and also accurate. Okay, with that being said, you can see here the base input and output paths have been set as well. So dataset, which is the basic input, and the processed images, where you can see the processed images as well. So if you go into the processed images, again, the images are classified into 3 structures, basically training, validation, and test. And only inside these, the images are categorized. So rather than going the other way around, this approach made it easier to import the files in a stream later on, which we'll get back to in a minute. Okay, so with that being said, after categorizing and also giving the respect ratios, we have basically created the 3 output paths: train, validation, and test, and make the necessary directories. And then it was followed by importing the image files, basically, which is followed by a JPEG. Although we didn't have to clean much of it, and all the files are JPEG, we have filtered it out just for the sake of more accuracy. So then the images are randomly shuffled before splitting them into respective categories, again to increase the accuracy and any possible overfitting in the end. Okay, with that being said, so number of samples, again image files, and the indexes for training and validation were split as well. And then through here, we have respectively categorized the images into those 3 sections: basically training, validation, and test. Okay, that's basically what's been done here, and the images are saved here again. Okay. So as I said, now we are in the training section of the model. So here we classify the images, and now we are moving on to the training section. So again, base path processed images, and we created the necessary directories. So here we are basically using the image data generator object, and we are creating a train data gen, which is basically train images. So the things we do, okay, rescaling. So all the pixels have to be rescaled, because 255 is the maximum possible values, and now we need to normalize it into a value between 0 and 1. So that's basically done here, and these changes are added randomly for each images, because it makes it better to avoid overfitting and again increase the accuracy by shifting the images and creating a dynamic rather than giving the static stack of images. Hence, in future possibilities, if image is received with slight distortion or shifting or flipping or whatever, then the accuracy of the model still prevails to be high, rather than directly feed in the dataset. Even though this data is somewhat clean, we've created some dynamic in the dataset, hence increasing the accuracy again. So once that object is created, now we are going to train generator, which is basically training images. So as I said earlier, the reason for like grouping these images in this way was to like make it easier for this function to call images in a stream flow from directory. So now we are getting the trained dataset, all the images, and then passing them on and getting into this function object as well, and then basically augmenting the images. So what's done here is basically the image augmentation. Okay, so with that being done, now we are moving on to the validation part as well. So in validation, we don't need to create this kind of dynamic here. So all we are doing is normalizing it again into value between 0 and 1 on each pixel. So once that is done, again we are getting the feed from the respective directories, and then targeting size and resizing, and then augmenting those images as well in the necessary state. Okay, now we are going into the core part of the program, which is the basic model. So this is the neural network that we've created, and basically followed by four layers. So basically on the start, we are converting it into 32 neurons on 4x4, and we were activating it based on a rectified linear unit. And again, the input shape is given as 2 to 4, which is the basic pixel 2x2, and the 3 values in each pixel, which is basically the RGB again. So here we get a 3-dimensional matrix. So that's what we are working on. And once that convolution is done, basically, then we move on to max pooling it using a 3x3. So this makes it easier to bring down the size of the whole thing, but also makes it easier for the next convolution to work on it as well. So on the next convolution, we are adding a layer of 64 neurons, again 4x4, and activating using ReLU. So once that is done, we are max pooling it again back to 3x3. On the next step, we are again converting it into 128 neurons this time, again increasing constantly, again 4x4, activating ReLU. But on this time, we are max pooling it into 2D using 2x2, and hence making it a little smaller again. So on the final convolution, we are converting it to 128 4x4, same as before. And once that is done, we are flattening the training, hence like bringing the dimensions into single dimension. Okay, so once these steps are done, then we are moving on to the densing of the layers, and again we are using 512 neurons this time with the ReLU, and this is quite a large amount of neurons. So now we have to address the overfitting of the possible cases. Hence we are cutting off 50% of the neurons that were created, and hence deleting all the paths as well. So it is somewhat costly on the side of accuracy, but again we have to clear out any possible overfitting as well as much as possible. Hence 50% standard rate is used. And once that is done, we are again densing it into 4 neurons basically, which represent the 4 categories that we have gone to, and we are getting the softmax, like basically the neuron with the highest possible probability. So that's a basic model here. So this is the basic front running path. So once that is done, now it's clear that the one with the highest possibility is chosen. But now we have to backtrack and like fix it, so like we can get the highest probability that is probable. Hence we are incorporating a learning rate of 0.001. Again, this is a trade-off, but with this value, like we identify that accuracy is quite high. So with those metrics in mind, this is the basic model that's been created, and the hyperparameters are as given, the learning rates and types of number of neurons that were used in each and every step. So that's a basic model. And once that's done, we also wanted to address any future possible overfitting as well. Hence, these two functions, which basically identifies when plateau is occurring on the accuracy, and hence decreasing the learning rate even more, hence giving the possible outcome of increasing accuracy. So hence that's what this section does basically. So you can see here, so like once this starts running, this is a basic accuracy. So value accuracy, you can see it starts off with a 0.96. Hence, as I said, like this was quite a good set of hyperparameters to be chosen in this case. So hence we started with quite a bit of high, like 96% accuracy. But it's also clear that once the process is going on with dropouts as well, the accuracy drops a little bit. And now this section triggers, and hence further decreasing the learning rate. And now you can see a rise in the value accuracy as well. So 0.96 here, 96% accuracy. And now, like up to this point, we can be quite sure that this accuracy is going to prevail and not go down rather than on the first go itself. So, but again, we are decreasing the learning rate, which you can see here, 2.7 times to the minus 5. So then you can see the accuracy is somewhat rising, 0.97, 97%, and it goes on and on. Again, we decrease the learning rate, and towards here now it should be visible that it's hitting a plateau quite a bit, and it's not increasing any further. So our peak accuracy revolves around 98%. So that's what we are dealing with here. Okay, so now for the sake of graphical representation, we have plotted these values as well, the loss in training and loss in values. So even though these two graphs may appear quite a bit far apart, it's because the difference of values has been chosen for the y-axis in a sense is quite a bit small. So this is a quite a good graph in my opinion. So in our opinion, that was the best we could work with. So hence the validation process is done as well, and it's validated that the training section is going on quite good. And then it's followed by the validation accuracy and the accuracy of the model, and hence again quite a bit two close graphs, and it's evident that the model is working as expected. So once that's been done, this is the basic summary. Again, the layers that we incorporated into the model, convoluting in these parameters, and then pooling, convoluting again, pooling, and followed by 3 such steps, followed by flattening and addressing the dropouts, and then densing and densing. So this is the basic summary. So total parameters that were used were 4 million, 390, and 052. So that's the case as in here. So with that being said, and then so down to here, now we address the training section of the data set and also validation process as well. Now we are moving on to the actual testing. So we get the test image paths, and we get the images here and loading them to an array, and again resizing them as well to 224, which was the trade that we took, and then loading the images into an array and expanding the dimension of the array basically in an array of arrays, and then normalizing the array again to a value between 0 and 1. Okay, after that we basically predicted the image array, and then we get the argmax of the predictions, which basically returns as I've discussed earlier, like the final dense layer denses it down to 4 neurons, and here what we are getting is the one with the highest possible probability. And once that's been taken, we check it with the initial category section, to further see if that indeed matches it, and then moving on to categorizing the tested image as one of the categories. And hence we check if it is in fact correct prediction or wrong one, and thereby increasing the respective part. So the process you see here as well. So once that's been done, we will finally plot out the correct predictions and the wrong predictions, categorized by each category. And again, for sake of graphical representation and for the presentation purposes, so this is what we are working with here. So with the 10% of the testing data set that we used, category 1 we were actually gotten 95.7 accuracy, category 2 again 95.7, category 3 98.4, and no tumor 98.5. So the overall accuracy revolves around, as I said, 97.6 or rather 98%. So that is the model that we created, and this is the general code overview of the section. So on a final note, this is the model that we created, and what should be emphasized is the augmentation part of the images, neglecting the fact that the data set is quite good. We augmented it as well. Hence we are confident that no matter what image is given, this data model is quite capable of handling itself and outputting a highly probable, accurate categorization, which is also been proven by the validation part as well. So I think that's about it. So in this section, I'll give you a brief overview about the deployment plan that was in mind. So basically, we are getting the MRI scanner, and through image scanning service, we are getting the images into image sending service, which is locally hosted, and then we are transferring those images into a local server, which is basically situated at the hospital or at the station that the system is being implemented. And then on the local server, the image sending service takes the image and then it's transferred into server service as well. And you can get additional functional like report building services as well. And again, they are connected with the server service, which is a remote server, which acts as the basic data center. So that's a basic data handling part. And then on the local server, we have the analysis service, which basically does the analyzing of the image with the model that was shared earlier. And on this analysis service, we get the image to be analyzed, and then that image is sent to DNN modeling service, which is on the remote server. And through this request call, the image has been sent, and then we get the verification of the categorization in which the image belongs. And once that analysis is done, then it has been redirected into a doctor's service where they get the alert of the possible conditions, and hence on the doctor's service we get the consulting service as well. And all these services are directly connected with the medical database, which is also remote again, and hence the doctor gets the facility to advise the patient as well. So, or alert the patient, advise the patient, and carry on with the procedures as required through the prediction that's been given by the model. So this is the basic deployment strategy that's being used. And we also thought about scanning the images through mobile devices as well, and hence incorporating this whole system into a mobile app. But again, it might cause some loss in accuracy, and some issues like that may also occur. And with that in mind, we did not get it here on this instant. But right now, the deployment strategy is, as I explained, the MRI scanner is getting it and transferred to a local server, which basically stores the images and do all the things. And then through analysis service, the needed image is analyzed with the help of a DNN modeling service, which is located at a remote server. And hence, if the result is taken, and then the doctor is alerted, and the doctor gets to see the analysis, and with this experience and knowledge, then they get to alert the patient. So this is the deployment structure that we created for the requested model.